Welcome to our lectures on DC microgrid system. We shall continue to our discussions on the remaining portion of the AC microgrid, then we shall mostly discuss on the DC microgrid. Let us revisit that last portion of the AC microgrid. So, we have already discussed that it is a grid feeding unit, and these grid feeding units are operated by the current control mode as a normal grid connected DES. Now, we shall come into the term with the grid supporting unit. So, in case of the when it is connected in a grid connected mode, this unit are controlled to extract maximum power from the primary energy sources and the required reactive power to support the grid voltage sag and local demand and the reactive current requirement. So, this will help us to increase the stability of the major grid. So, it will supply, it can act as a sag control, and it will supply the necessity whatever the reactive power required to be fed to stabilization of the grid. So, because if you have a then this grid is ace of doing that control, microgrid can take care of the reactive power flow control, then it just can concentrate on the real power flow. Thus, the AC voltage control method with repetitive control loop to compensate selective harmonics was applied. That can be one of the applications, that is the THD or the power quality issues, along with the modified MPPT algorithm, so that it can dispatch the maximum power to the grid. So, let us see that overall functioning of the microgrid with the grid interaction. So, this is the grid forming units, functions, these are voltage and the frequency control, and sometime load sharing, hybrid AC voltage and current control, indirect current control and AC voltage control. These are the different kind of control we may use. Then we got a load sharing, the frequency and the voltage control, and active current sharing, thus by active power sharing. Grid feeding unit, that is power dispatch and the real and reactive power support, current control and voltage control both, that is VOC and virtual flux control and direct power control. This can be a different kind of control technique can be applied. The real and reactive power support, the control technique can be unity power factor control or the positive sequence control if it is unbalanced also there, and constant real and reactive power control. Grid supporting unit, real power output, that is MPPT, and PQ support, generally it is AC voltage control. This is some discussions on the AC microgrid. Now, we shall switch over to the DC microgrid. So, while in a DC microgrid, we will discuss about the introduction to the DC power system, and we shall see that what are the difference Edison proposed, and now this is DC microgrid. And motivation for the DC microgrid system, even though world's done in AC. Principle of the DC voltage control, we have seen a different kind of voltage control is been described in case of the DC. Now, AC we will see that what can be done by DC. The DC this is the DC microgrid power flow control, practical concern of the future microgrid system. These are the few things will be discussed here. So, the first electrical network was designed to operate with a DC power. We all know that by Edison. However, due to the practical challenges to implement with practical challenges with the implementation of the DC network, for example, absence of stepping up and the step down voltage level, which can be easily done by the transformer level during that period, made the utility company to shift from the DC to AC system, mostly due to the transformer, because at that time we did not have a very versatile SMPS or switch mode power supply or DC to DC conversion system. For this reason, you are forced to go for the AC system, and it has a lot of advantage of the AC system, we cannot deny that. One of the main reasons for worldwide extension of the AC system is the possibility of the voltage level conversion by use of the AC transformer, and it has a very high efficiency, it is quite rigid, resilient, it is a long life. For this reason, AC takes a case for transformer, whereas change in the level of DC voltage require implementation of more complex power electronics devices that were not available in the past, and so Nikola Tesla win the battle because of the lack of DC to DC converter in those days. However, in the recent time, new and efficient converter have been developed that facilitates the changes of the DC level. We can have multiple DC level with the help of the different type of DC to DC converters. Using this new development, almost all the required DC levels and current levels are available by use of series or parallel structure of new power electronics devices. Today's digital age, more and more devices are operated with DC power. For example, consumer electronics, industrial information system, communication technology and electric vehicles. So, for this reason we have huge chunk of the DC power, and also we have a DC sources. The microgrid is an electrical system that can efficiently distribute, consume and potentially create and store direct current electricity to power a wide variety of electrical devices in and around a building when connected to a utility grid or as an island. A DC microgrid comprises of DC power sources, PV, wind, fuel, rectifier connected to the utility grid, the power distribution networks, SAPE, class 2 wiring, conduit wire, DC devices, load, lighting, computer, electronics equipments, controls, motors, fans, etc. Controls and monitoring of wireless, wired, virtual, cloud based computation, servers and other devices. So, this is the advantage of the DC microgrid, it is shown here. So, this is the DC microgrid loads, that is VFD, variable frequency drive. You may have a solar panel and you have only 2 to 5% loss, and thus you have a DC grid. From there you can have a CFL, you can have a computer, you can have a DC batteries to run the car. Thereafter you may have a storage element, and you may actually get the power through active rectifier inject into the system. The higher efficiency, so we will, what is the cause for going for the AC? one is higher efficiency, and you have seen that different kind of reactive power, real power flow to be controlled. There are many issues, frequency, drooping, all those issues comes into the picture. Minimal conversion loss, we can see that this is the active rectifier, loss is just 3 to 5%. Lower operating expenses, because you can actually get rid of bulky transformers and a transmission line. It is safer, generally peak of the AC is is actually root 2 times more than the peak of the DC voltage, since RMS values are set 220 volt DC and the 220 volt AC. AC is more fatal than DC, and fewer components, because you need not have to, if you require to have a adjustable speed drive, just since your DC bus is available, you put an adjustable speed drive and charge it, you run it. More reliable, essentially these aspects required to be proved of resiliences of the DC to DC converter. Nowadays we are moving towards all this pressure on the DC to DC converter, and our designer can make more resilient DC to DC converter. For this reason it can be more reliable. Less real estate space you will occupy, because you not require a bulky transformer, and reduce carbon footprint, since you can use solar directly. So, these are the those are the few aspects of the DC microgrid. Then see the motivations for the DC power system, and you know that to meet the transmission losses nowadays, you talk about the HVDC line. Now, you may have a very high voltage DC line, and from there you can have a mega voltage bus, and from there you may have a AC microgrid, you have a wind turbine, then we may have another AC microgrid, and here this portion is the DC microgrid. Same way you may have a photovoltaic cell. Photovoltaic cell is DC, you can convert into the AC and connect to the some AC buses. Thereafter, from there you can have a photovoltaic plant, again you inject in AC. You may have a energy storage system, again you have to convert into the AC. You have a wind turbine system, you have a AC, thereafter you convert into the DC, because you cannot integrate directly to the frequency that available from the wind turbine because of the fluctuations of the wind speed, and ultimately you got a DC to DC conversion here, and then you put it, and this part is also DC, and again this part is DC, you have a DC to DC converter, then you have a AC to DC converter to synchronize. So, what we can see, essentially this AC to DC converter is placed in everywhere. So, why can't we get rid of this AC to DC converter and thus increase the efficiency and the reliability of the system? As shown in the figure 2, the native DC generator sources are connected to the AC grid through interface converters. In this case, 2 power converter stages are required to connect distributed generator to the AC grids. So, we can get rid of this extra AC to DC converter every places by having a DC grid. And see that as shown in the figure 3, the number of the energy storage are reduced in the distribution system. Consider that DC distribution system, you have a solar photovoltaic cell, you have a DC to DC converter directly put to the DC bus, you have a DC load and electric storage element that can directly coupled, and you have wind turbine, you have a AC to DC conversion and directly put it, and again you have a solar photovoltaic cell, you can directly put it to a DC to DC converter. So, you get rid of many AC to DC converter, and here you can see that you have put this AC to DC converter. So, you can see that number of component count in DC microgrid essentially are less. So, number of energy conversion stages are reduced in DC distribution system, hence DC systems are an economical, since you have a less component count, reliable solution for the DG integration in case of the microgrid. Now, increase the transmitted power by a cable. So, this is the challenge, you do not have a transmission line here in the case of the microgrid. Power carrying capability of the AC line depends on thermal limits and required reactive power, while capacity of DC line mainly depends on the thermal limits only. Due to absence of the reactive power current component, the current magnitude of cable losses are reduced when DC is used. To illustrate this fact, let us consider the current flow in the line that can supply given AC and the DC voltages. In AC system, assume the load is single phase load, that is PAC cos phi and IAC, its active power, power factor and current when fed from the AC source. The corresponding line current can be calculated as this one, that is IAC equal to PAC by VAC into cos phi. And whereas in case of the DC, where AC is the root mean square or the RMS value of the AC voltage, the current of the supplying load by DC voltage is just IDC equal to PDC by VDC, where PDC is equal to the active power when the load is supplied by the AC sources, and DC is the voltage that can be considered to be root 2 into VAC. Since insulation of the cable and the insulation is designed according to the maximum voltage of the AC system, the load can supply by the DC voltage equal to the maximum value of the AC system. So, you can go to root 2 times higher to supply the power, thus cable can handle in terms of the insulation higher DC voltages. The current flow through the line is connected to the DC source can be calculated by cos phi by root 2 into IAC if cos phi, let us assume something. So, it is 0.87 is assumed, the DC current cable is 60% of the current of this line when load with the same active power is supplied by the AC source. So, 60% current rating is diminished, so thermal limit you can push for the higher current capability. This shows that the total power of load that can be supplied by the cable increases when DC systems are used. So, let us come to the figure 4. Principle of there is no frequency control, only there is a voltage control. This is one of the also a big advantage of the system. Figure 4 shows the basic DC terminal model. The terminal voltage would rise when capacitor charging current is positive and drop when capacitor charging current is negative. The voltage variation of DC microgrid can indicate whether the system power flow is effectively balanced. So, you have the capacitor voltage, when you see that this is only the droop control, when you can see that voltage of the pass is constant, that means power input and power output are being balanced. The charging current can be mathematically expressed by I charge equal to I t minus I g. So, from there you can control the flow of the power in microgrid. This is a simple model. So, principle of the DC microgrid voltage control, there is no need of the frequency and reactive power, real power control. This is the droop control. We have seen the droop control in case of the frequency control in case of the AC microgrid. Here we can apply the same concept but it is quite easier. It does not have a VCO and all those things. You can directly fit Vref and Vt. You have a delta error, then you may have a proportional plus integral control, that is PI controller, and thereafter saturation block, and you can calculate the IT that required to be charged this capacitor. But IT is the terminal current and Ig is the grid current. Once grid current is given, the charging current can be regulated by controlling the terminal voltage. Droop control, as shown in the figure 5, is widely used in implementation to determine how much current a slack terminal shall given in a real time basis. Please recall your power system analysis, you have a slack buses. So, that in this case we have a slack terminal. Linear current voltage control is imposed when voltage variation varies between V1 to V2. So, you can have a linear control, works very fine in this system. Saturation current or voltage is normally added for the power rating or control band switching concern. The droop control can also be generalized as proportional with the saturation control as shown in the figure 6. So, you can go back to the figure 6 and can see this is basically the droop control and this is the saturation block. Now, come to the point of DC microgrid power flow. The power flow control capability is one of the main challenge for successful operation of the DC microgrid. The DC network and the bus voltage do not have a phase angle and the transmission line impedance do not have the imaginary part. So, it is quite simple. So, you have a DC source, you may have a DC to DC converter because this DC source voltage and the load voltage may be different, and for this reason you have a different VDC, that RDC, then VDC minus del VDC, and this will be the load. Now, the current, voltage and current are only parameter used to control the DC power flow. Now, in DC grid, the active power flow is proportional to the DC voltage, that is VDC. Therefore, the active power can be controlled by the DC link voltage as described by this equation, that is actually this P equal to DC del VDC by RDC, where del VDC is the voltage drop over the line resistance RDC. In DC grid, increasing load decreases the voltage of the DC link capacitor CDC. Now, come to the last issue, this is a protection issue. So, protection is one of the main concern about implementation of the DC microgrid. Protections issues are mainly caused by particular behavior of the fault current in the DC network. Of course, there is this issue is quite challenging because in case of the AC you have a zero crossing that is missing here, and thus you require more current carrying capability, more stopping current capability to stop it. And because the impedance of the DC line are lower, this is also another demerit than the AC line's counterpart. DC fault current increases very fast, and this may disrupt the conventional overcurrent relays. So, it has to act very fast because since there is a inductance in the line, current will take the time to grow, but in absence of the inductance current will go in a steps fashion. Alternating current circuit breakers, ACCBs clear the fault during the zero crossing. That is what I was trying to say, zero crossing point of the fault current waveform. However, there is no natural zero crossing in case of the DC current. Therefore, new fault interruption devices are necessary for the DC network. Accordingly, uses are behavior of the converter under faulty condition, significant specification of the DC fault current, that is something we require to redefine it, fault detections, and sometime we have to have a fault tolerance system also. Fault detection and the fault current interruption methods are the main subject that require more research and development, because we till now we have a protection system keeping in the mind of the AC protection system. Unfortunately, we have a DC protection system. These are few challenges. So, practical concern and the future of the DC microgrid, power conversion and other efficiencies will give you a more in terms of the DC, but protection is one of the concern. So, in a AC microgrid, as we can conclude our discussion in this fashion, that in a AC grid, synchronous machine is the main device to provide active and the reactive power. Hence, modeling of the synchronous machine dynamic is the key to successful dynamic behavior assessment of the power system. That is what people used to do past 50 or 100 years. Similarly, the main component that exchanges power in DC grid is the power electronics converter. So, it has been replaced by first switching power electronics converter. The in comparison to synchronous machine, power electronics converter have much faster response due to additional control capability and much slower inertia. So, that is aspect some extent is bad, low inertia, but fast response definitely gives you more leeway. Thus, the modeling of the power electronics converter dynamics is a key of microgrid, is a key aspect for assessment of the dynamic behavior of the multi-terminal DC microgrid, DC or AC microgrid both, it is applicable for AC also. But due to their switching behavior, the dynamic equation describing the converter operations are discontinuous and complicated to solve. So, ultimately you will study little bit of DC to DC converter, and ultimately you may have a come with the different DC to DC converter in a discontinuous mode, have a become a minimal phase system, or or many complications on the control system point of view arises. Thus, this is a great challenge for the power electronics and control designer to solve it, and if you can solve it, then there is a huge potential for the DC microgrid. To simplify power electronics converter complexity, that is what I am saying, the average dynamic model can be employed, but it is an approximation. The advantage of using average model is that they simplify the converter analysis while still allowing enough detail to understand the dynamics depending on the control strategies. So, that phenomena actually because you have essentially a nonlinear control, because one states matrix will be there for the DC to DC converter when switch is on, and another state matrix will be there when switch is off, because it is on and off the power electronics devices that makes you a DC to DC converter. So, essentially what you can have a average model, and you may have actually a different kind of switching frequency based operation. So, average model is an approximation of this criteria, considering that non-linearity part is omitted, and you can apply the linear control there. So, stability is an important parameter. There is no reactive power flow, current and the voltage frequency component in the DC network. So, only the voltage control matters and the protection matters. Additionally, active power flow depends on the difference between the bus voltages, just bus voltage control will control the active power, and therefore, the stability of the DC microgrid, which depends only on the bus voltages, has to be analyzed in a different way than from the AC power system, which we used to do in a traditional load flow analysis. So, load flow analysis mechanism we cannot apply in case of the DC microgrid. More importantly, it has to include DC passive component and the power electronics converter and their feedback controller, and that worsens sometimes the control strategies. Thank you for your attention. We shall continue our discussion on the DC microgrid in our next classes.